We're talking about concept learning. I want to first address a email from a student who said that he didn't always understand me talking in class. I will try to speak more clearly, which is not to say more slowly. But I want to encourage you, if there's something you missed and you think it's important, you can not only go back to the recordings, but you can go back to recordings from a previous year, which I also have posted on the same schedule page. The leftmost column, the one that has the topics, has links to recorded lectures of the same course from a year or two ago. The examples I use are the same, the jokes are the same jokes, but the discussion, the class discussion is different. People ask different questions and we do go off on tangents. So it might be worth your time to try that instead of these lectures, or both. And especially if there is something you didn't understand language-wise. Maybe it's clearer in the previous one. Okay, so to remind you, the main take-home of concept learning is that a concept, unlike in everyday usage, a concept in machine learning is defined as a binary function. Binary function over some input space. Which I call big X. And hopefully I convinced you that binary function over some input space is mathematically the same as defining a subset over that space, or a subset of S. Namely the subset of inputs on which the binary function says yes. And another equivalence that's very important is this is the same as the bit vector of length the size of X. These all are mathematically equivalent. Example I gave is cities I love. Let me try to turn this down a little. This is X, and the size of X is 568. And now I can enumerate all possible inputs as X1, X2, X3, all the way to X568. Every function, every possible binary function over this domain can be represented by a bit string, a string of bits that assigns 0, 0, 1 to every possible input, which means that every bit vector corresponds to a concept. Now, this doesn't agree with our intuitive notion of concept. A concept over the space of big cities could be big cities in Asia, big cities in Africa, big cities that have more than 10 million people. These are concepts we understand. And they do correspond to a particular bit vector here, right? The bit vector for big cities in Asia would have 1s for all the cities that are in Asia and 0 everywhere else. So in our intuitive notion of concept, it has to make sense. And you can come up with hundreds of concepts that make sense. But there are many, many more concepts that don't make sense. They're just arbitrary subsets. So if I take any random bit string, if I just come up with a set of bits, I may not be able to describe in words a property that applies to those that have a 1 and not to those that have a 0. So it may not be a coherent concept from my way of thinking, but mathematically it is a concept. That's the point that several of you have asked me about after class. So by concept, we don't mean what it means in everyday life, namely something that you can think about conceptually, but any subset of the input is a potential concept. Okay, that's the second thing I wanted to correct. Okay, so I try to impress on you that the space of possible inputs is usually very large, and the space of concepts is usually much larger than that, 2 to the power of that. And then I gave you a specific example taken from Mitchell's book, where the space of concepts is the space of all possible weather conditions in a given city in a given day, as expressed by only these 6 leftmost variables or attributes. And you know that we already threw away a lot of information by focusing on these 6, because there may be other things that are not measured here. So just by deciding what features we're using, we are implicitly assuming that the answer depends only on these and not on something else. And that's a risk we're taking. But nonetheless, we're assuming that somehow the answer or the function or the concept depend only on these 6 attributes, and therefore the input space consists of all possible combinations of these. And we did a calculation that the first one has 3 possible values and all the others have 2 possible values, resulting in 96 different possible weather types. So x is 96, size of x is 96, and the size of the concept space, that means the number of bit vectors in this list would be 2 to the 96, okay? Which is a very large number. And now we're given 4 training examples. And we are asked, at least in principle, we are asked to search a space that's this size. We're asked to consider this many bit vectors and to choose one as our learned concept. And that seemed awfully hard to do. And then I pointed out to you that young children do it all the time. So now is the time to show you my favorite concept learning book. So this is called Find the Puppy, and it's for children who are about 1 year old. And the first thing you show them is this puppy right here. And it's, you see most of the puppy. You don't see their right front leg or paw, but that's good enough. And then, can you find the puppy here? Can you find it here? Yeah, you found it. Now, it's right here. First of all, it's not a puppy, it's a huff puppy. Second, think about its size. It's tiny, whereas the picture on which the child did the learning is huge. Okay? Now, you didn't tell the child, find a puppy in any size, right? You just say, find a puppy. You didn't tell them where to search for the puppy or what kind of occlusion might occur. And here's another puppy, another picture of the puppy. And here is only the head, right? It's not the real puppy. So somehow the child knows from the few examples that it should be size invariance, translation invariance, occlusion, small parts, and my favorite picture is this one. Is that a puppy? right here. Okay. When you are done doing this kind of learning, if you write a program to do that, I have find a kitten for you, find a duck, and find a piglet. My point is, children do it effortlessly with a handful of examples. And my question to you was, how do they do that? And you were supposed to think about it. I hope you did. How do they do that? Yeah?
So I think that programs are usually trained for one specific example, but children are trying to learn everything as much as possible without any boundaries or limits. So whatever they learned previously can be used for other examples as well. But in comparison, programs are just given a specific task and just have to learn from those specific examples.
Fair point. The point is that children don't learn just one thing. They learn all the time many, many different categories simultaneously, so they can share their learning. There's some elements that are similar. Of course, you know, if you learn a cat, you learn a dog, you learn other animals, they share a lot of things in common. You learn the concept of animal. In fact, even before that, you learn the concept of an object. The whole notion that there is such a thing as an object and that it stays in place and doesn't disappear when you close your eyes, so that when you open them, it's still there. That's called object permanence, and that's something that children learn at a specific time. I don't remember if that's 9 months or 7 months or something in their life, but there's a particular time when they usually figure out that there is such a thing as object and it exists in the world regardless of their perception of it. Okay, so there is something to that, but in some sense it makes the problem harder, because now you have to explain to me not just how they learn a dog, but how they learn everything at the same time. Yeah?
We try to find differentiating features, like in a dog, you see the eye and the black.
Right. So the answer is they try to find differentiating features. And we all know that's true to some extent. We find features. Our machine learning programs find features, but people find features too. It makes sense that they work by features, because like the stuff around the eyes is something that exists in most of these pictures. But mathematically, it actually makes the problem worse. I'll tell you why. How many features are there? How many potential features are there? What are features, first of all? What are features?
Distinctive characteristics.
I'm sorry?
Distinctive characteristics.
Yes, but mathematically or computationally, how do we capture them? There are functions of the input, right? Right? Like either the feature is there or is not there. So what kind of functions are there? Well, there are binary functions of the input, and maybe also to specify not only is the eye there, but where it is. So every feature is a binary function, maybe plus localization, right? How many features are there? How many potential features are there for the child to choose from? Yeah? Number of pixels. That would be true if every feature will correspond to a pixel. But features could correspond to combinations of. We said that features are binary functions, plus some extra localization information. How many binary functions are there? That's the one thing I taught you so far. How many binary functions are there? 2 to the power of the size of the input, right? So there are as many features as there are functions to learn, to choose from. So how do you I mean, you're just begging the question. How do you choose one of these functions? By learning features. Well, which features should you learn? Every potential binary function is a candidate feature. So features in AI have this weird property that if you solve the problem of finding the right feature, you solve the AI problem. Okay? Here's a feature that I'd like you to learn. Whether there's a dog in the picture. That's a feature. Okay? So you can think of features as halfway or part of the way towards solving the full problem. And the mathematical problem of finding the right feature is as difficult as the mathematical problem of solving the whole problem. So yes, there's truth to that. This is how we use it, but it doesn't solve our mathematical problem of how do you choose from such a huge set. Yeah?
Yeah, we pick out the right feature by by computer, how well this feature can differentiate the object from others.
Okay, so we pick up we select the right features by looking at how well they differentiate this picture from others. Specifically, how do they differentiate pictures in which the dog appears from pictures in which it doesn't appear, for example. And we try all features and see which one has the best differentiating power?
No, we will not try all features, not possible.
No, we can't try all features. So which features do we try?
I think that the first step may be method, but we have to find.
So maybe at first we try some at random, but maybe after that we use some heuristics by features. Okay, where do the heuristics come from? When did the child start learning what a dog is?
After seeing one.
I'm sorry?
After seeing one.
After seeing one. That's one answer. Somebody wants, yeah?
What if through evolution we have some sort of stored feature sets and we are kind of invoking some form of transfer learning?
So I'm happy to have heard the word evolution there. When you said, when I asked when does the child start learning dog, I was hoping somebody would say the moment they're born, and somebody else would say maybe millions of years before, right? Because evolution is a form of learning. And how exactly we do it is a separate story, but there is some amount of learning the hard way, that goes on during evolution, such that when a child is born, they already have some structures in their brain that are pre-tuned to certain things. I don't know exactly to what, to objects, to animals, to furry animals, to animals with teeth, you know, whatever they're pre-tuned to. Yeah, evolution certainly is a large part of that. The child didn't really start learning when they saw the first picture. The process started a long time before. Does that solve our problem? I don't think so. I don't think it solves a mathematical problem, but it sort of provides partial solution, perhaps. All right, I'm going to write here the standard framework for concept learning, which I've written several times before, but I want to sort of reinforce it. There's an input space, X. It has all possible inputs in it. There's a concept space. And the size of the concept space is always 2 to the size of the input space. Then there is a target concept C, which is a member of big C. We call it the target concept. You can think about it as one particular bit vector here. Now the thing is, we don't know what that C is. We know it exists and we're trying to find it. But we don't know it. Unknown. To us. And the next thing we said we have is training data, which the way I wrote it confused some people, so I'm going to clarify this. I can start writing it as pairs of x1, y1, x2, y2, xn, yn. So these are n pairs of inputs and outputs, as you saw in the example. Oops, I can put you back. Now, I'm assuming that the examples have no mistakes in them. Specifically, there are no errors in the labels. And because this is the little c is the target function, I can write every y yi can be written as c of xi. That doesn't mean I know the function c. I don't know the function c, and therefore if you plug a different input into c, I will not know what the answer is. Not yet. But I do know that whatever c is, it satisfies this condition, because I was given training examples and I'm assuming there's no mistakes in them. This is why I allowed myself to write, instead of y1, c of x1, and instead of y2, c of x2. Okay, so I don't know the function c, but I know its value on the training examples. All right, so in this case, our space is very, very large, and we have only 4 training examples. What I'm going to do next is, instead of trying to find the correct c, I'm just trying to find a function that agrees with the training data. Okay, there's a slight conceptual change here. My original goal was to find the true function, enjoy sport. I'm going to back off and say, let me just try a function that agrees with my training data. If I find such a function, is it guaranteed to agree with future data, to be correct in future data? No. So why am I bothering? My goal is not the exercise of finding something that agrees here. My goal is to do well on future data. If I find a function that agrees with the training data, do I have reason to think it might? Yeah. Why? Why do I think that if it agrees with the training data, it's likely to agree with future data too?
Maybe the training data is large enough, so it will cover all the possible, not all of the most possible cases.
If the training data covers most cases, or all cases, then I don't have a problem at all. If it covers most cases, remember how many cases are there? 2 to the 96. That's 10 to the 30. So the training data is not going to be, I'm sorry, 972. So we're not. If we have all 972, then we have nothing to learn, right?
We made the assumption that our test cases are valid, which means so like y is automatically a c of xi, and therefore since we know the output to that specific input, in which case we can assume that since we have that example, that it's going to be correct.
We can assume that since we have these examples, that the output is correct, but my question is about future examples, things we haven't seen yet. If I find you a function now that agrees with these 4 examples, that produces yes to the first one, yes to the second, no to the third, and yes to the fourth, do you have a reason to believe that if I give you now a new input, new weather pattern, that that function will give the correct answer to? I'm sorry? Not necessarily. I think we agreed that not necessarily, and we also agree that there's a good chance, or there's a good reason to think that. But my question to you is why? Why do you think that because we did well on the training examples, we'll do well on future examples?
So these are all real-life examples in the test. So unless something drastic changes in the future, it's very likely that we'll follow the same trend of the, for example, we're talking about weather patterns here for enjoying sport. So if we have enough training examples and we decide that, okay, you're likely to play a sport if the weather is sunny and warm, that's not really likely to change in the future. It will be somewhat derived from our present understanding of the...
So you're saying because the examples are typical, they're really derived from the real world, that's the reason for that? Well, let me give you a function. Remember, my question was, if I find a function for you that agrees with these, do you think it will agree with future examples? And let me give you a function that agrees with these. The function says, look at your new training example. If it's one of these, give one of these answers, the correct one. Otherwise, say no. That agrees with these, right? Let me give you another one. Look at these training examples. If it's one of these, give the correct answer. If it's not, say yes. Also agrees with the training examples. Now you told me these two functions couldn't be more different, right? They disagree on everything else. And you told me that you expect that they will both be correct. Now that can't be. What we're trying to do here is called induction. Induction is the idea of generalizing, inferring from what you see to what you have not seen, and it is not a mathematical theorem, it is a principle that can definitely be violated. You can call it the induction principle, as opposed to deduction, which is the logical conclusion from premises to conclusions. And the premises are correct, if the conditions are correct, the conclusions must be correct. Induction has been the topic of hot debate among philosophers for hundreds of years. Induction is not guaranteed to work, and still it's a very useful concept. You know, we all kind of agreed, and you all gave me different reasons why it should work. The funny thing about induction is that it worked very well so far, so we think it will work in the future. But that's an inductive assumption too. Yeah?
There's sort of a related concept called abduction. I haven't heard of it until recently.
I've heard the term, I'm not sure. I don't remember what it means, I'm not sure. Okay. Now, are there conditions under which you would be suspicious of induction? Are there conditions under which, even if you have a lot of training examples, you would not trust your output? Yeah?
When we basically make an assumption that the function is smooth. So there could be like training examples where at a particular point the function just shoots up somewhere, which we wouldn't have got in our training examples.
You're saying that when you have reason to think the function changes abruptly, then you may not trust your training examples. Okay, let me convert it to the domain of time. When the phenomena you're studying is time variable, it changes over time. It's a moving target. Then what you learn from your training data may not be, as applicable to the future. Okay, that's it is kind of what you said, only in a particular domain. Here's another case. Suppose the function doesn't change over time, but the input distribution does. Suppose you learn the function that is correct 99% of the time. So there are some inputs on which it doesn't do well, but they occur rarely, 1 in 100. That's not too bad. But next month, the distribution of inputs, the source from which your inputs come, changes. And all of a sudden, that area that the function doesn't do so well on shows up much more often, 20% of the time, 50% of the time, 70% of the time. So a function that was doing well, that was a good approximation of the true function, can all of a sudden overnight become a bad approximation of the true function without the true function or the approximated function changing. What changes is the distribution of inputs. Which inputs are more likely, which inputs are less likely. That's another example. Okay, so let me move on because I want to get to some topics before the end of today because I want to release your assignment. We still have a problem of only 4 training examples in a very large concept space. And what we're going to do to make our life easier is make some assumption about the form of the solution. We're going to assume that the solution is a conjunction. Conjunction means and. So we're going to assume the solution, that the correct function is something like the sky is sunny and humidity is normal. Or the sky is rainy, the temperature is warm, and the water is cool. Or humidity is high. That's also a conjunction of one conjunct. Okay? So as long as I can express my hypothesis or my function as a conjunction, as a set of conditions, one or more conditions, then I will consider it. Otherwise, I won't. My first question to you is, are there functions that cannot be expressed as conjunctions? Everybody's clear on what a conjunction is, okay? Humidity is high, and, this is my symbol for and, temperature is low. Is temperature low one of the things here? Temperature is cold. This is a conjunction. It means when I get a new training example, I'm only going to look at these two attributes, humidity and temperature. If the humidity is high and the temperature is cold, I'm going to say yes. Otherwise, for anything else, I'm going to say no. A conjunction could have two conjuncts, as in this case, or 3 or 4 or 5 or 6. It can also have one conjunct. It could also have 0 conjuncts. What does it mean for a conjunction to be empty?
True in all cases.
True in all cases. Why is it true in all cases? Because you can think of every conjunction as if it says yes and all of these conditions. And when all these conditions are gone, you're just left with a yes. So conjunctions is like a product that you start with 1. Okay, so back to my question. Can all functions, all concepts, be expressed as conjunctions? Okay?
For instance, the function, the temperature and the water temperature are the same, cannot be expressed as conjunctions.
So you're saying the answer is no, and you give me an example. The function that checks to see the water temperature and the air temperature. So this is the air temperature, and this is the water temperature. The function that checks to see whether they are the same or not, and says if they're the same, I'm going to enjoy sport, otherwise I'm not, that cannot be expressed as a conjunction. That's true. So there's at least one function that cannot be expressed as a conjunction. Yeah?
So to just clarify, a conjunction is a Boolean function that only uses and?
A conjunction is another word for an and. Yes, it's a Boolean function that uses only and. 1 or more times, or 0 times actually. Yes?
So the examples you gave while trying to prove that point, that I give yes for these examples and no for everything else, or yes for everything else, those can't be framed as conjunctions.
They probably can't. We didn't quite prove it. I didn't prove your example, but I agree with you. They can't. Any other examples? There are so many functions out there. Just choose one. An or of 2 or more conditions cannot be expressed as a conjunction, as an and. So an or is called a disjunction. Okay? Here's a quick way of seeing not only that there are many, many functions that cannot be expressed as conjunctions, but that most functions cannot be expressed as conjunctions. This is called the counting argument. How many functions are there overall in this space? 2 to the 96, also known as about 10 to the 30. How many conjunctions are there? How many different conjunctions? Well, when you construct a conjunction, you have a choice. You have multiple degrees of freedom. You can include the first attribute or not include it. You can include the second attribute or not include it. You can include the third attribute. For every attribute, you can choose independently whether you include it. Furthermore, if you choose to include an attribute, you can include it with any particular value. You can say the sky must be sunny, or you can say the sky must be cloudy, or the sky must be rainy, or leave it out. Not have the sky in the conjunction. That means you have 4 options for sky. The 3 values and not including it at all. And then independently you can choose to include temperature with insisting the temperature is warm, insisting that it's cold, or not including it at all. So this gives you 3 options there. And you have 3 options for each of the others. And I think this comes to 972. I think it does. That's what it did last year. This is the number of conjunctions. Now compare this to this. It's a little smaller, which means the vast majority of functions cannot be expressed as conjunctions. So if you create a function at random, and how would you create a function at random? You would go to the table of bit vectors, and you would select one of these bit vectors as random. Just select one of them. Chances are it cannot be expressed as a conjunction. So if you now conceptualize the space of all possible concepts, so this is now C, not X. Remember we had X here. This is the input space. This is concept space. Which is larger? By a lot, right? It's exponentially larger than this, but I can't draw exponentially larger on the screen, so on the board. If this is the concept space, the set of functions that can be expressed as conjunctions, the set of functions that are conjunctions, is a tiny, tiny subset of it. Really tiny. So by making this assumption, we are throwing out of consideration the vast majority of functions. Should we do it? Yes? Why?
Because the concept space is really big, and if we don't, we'll never find the answer.
You're saying we should do it out of necessity because the concept space is so big and we have so little data that we must restrict ourselves, otherwise we will not find the answer. Okay? Yeah?
We have a prior belief from our experience that it's a reasonable thing to expect.
Thank you. So one argument for why we should do it, because we have a prior belief from our experience that conjunction is a reasonable way of expressing the answer. What happens if the answer is really a disjunction? It's simply, or the example you gave earlier, that the temperature must be the same between the water and the air. If the temperature is the same, I'm game for playing sport. If it's not the same, wake me up tomorrow. That's a reasonable answer. Well, as far as any reasonable answers are concerned. What if the answer is, at least it has to be either the air has to be warm or the water has to be warm. Otherwise, I'm going to be too cold. That's a disjunction. It's not expressible as a conjunction. So if by making this assumption, we may be throwing away the correct answer. So that's a dangerous move. Should we make it? If we don't make this assumption, we won't have anything at all. So it's better to make it and close our eyes and jump. Well, but do we have to make this assumption? Why not make the assumptions that the answer is a disjunction? It's kind of a symmetric situation. Disjunctions and conjunctions are very similar. There's as many disjunctions as there are conjunctions. So it's also a very small subset of the space.
conjunction is we first consider each x separately, like we try to determine whether the x is related to my answer, and then probably we could select a subset of x and try to see whether the combination of them have some relation between our output and make more sense.
Okay, I love the answer, especially the very first part. Let me repeat that. First, look at your inputs, or your attributes, I think is what you had in mind. Not the x's. By x, we mean the entire row. I think you meant the attributes. And consider whether we think they are relevant to the answer. And if we think they're not relevant, get rid of them. I think that's very powerful, because by getting rid of one attribute, we're cutting, if we got rid of a binary attribute, we're cutting the input space in two by half, right? And then we're cutting the concept space by a much, much larger amount. We're significantly reducing the size of the space. So one take-home message here is that the more features, the more covariates, the more attributes, the more variables you have to start with, the larger the space that you're searching of solutions. So you should maybe scan it first and try to reduce it if you feel confident that maybe some of these attributes don't have anything to do with the answer. The second part I kind of agree less with, because you were saying that you're going to sort of see how related they are, or which are related, or maybe you want to rephrase that?
For example, if our output doesn't depending on the temperature, but depending on the relation between sky and temperature. So the second stage is like we try to make a function between the output and the relation between two or more.
Okay, so you were suggesting we test different combinations of small number of our attributes. In your example, 2 attributes, but notice that there are a quadratic number of combinations of attributes, right? And that only looks at values of 2 attributes and whether they are related to the output. And you may want to look at 3 and 4 and 5. So it doesn't quite solve the problem, but I agree with you, it's a reasonable heuristic. I want to go back to this notion of, did we make the right choice when we chose conjunctions? Yep.
I think that if you do like conjunctions, then when you have no answer, you one short of it, versus if you do disjunctions, then you have a yes answer. Or like maybe someone's off, but like a conjunction will get less yeses than a disjunction.
A conjunction tends to get more no's because it's a very restrictive, this has to happen, and this has to happen, and this has to happen. That is true. And a conjunction tends to get more yeses.
So I was thinking that maybe it depends on whether you care more about being right out of the yeses versus.
That's a very interesting answer. So since conjunctions tend to be more restrictive, they tend to give more no answers, and disjunctions tend to give more yes answers, ask yourself, do you care more about making mistakes one direction or the other direction? The point I was trying to get to is that there is no mathematical answer to the question of whether we made the right decision here with conjunctions. There is no machine learning answer to that question. The answer you try to give me, which I appreciate, we will use later to further narrow down things from the 972. But the initial choice of restricting our consideration to a very small set is done before we saw the data. And the only way to do it is by thinking about the domain, thinking about the problem, and what you think makes sense or doesn't make sense. And secondly, a very good point, thinking about what matters to you. That process of bringing down the space is called inductive bias, related to this induction process that we're doing here. Inductive bias, now we're used to thinking of the word bias in everyday language as a bad thing. In machine learning, inductive bias is not only not a bad thing, it's an absolutely essential thing. It's a necessary thing. You have to have a bias in order to learn. If there's one sentence or one idea you should take from this course, it's exactly this idea. In order to learn, you must have bias. We're going to see this notion of inductive bias coming up in other contexts and different formalisms. They all mean the same thing, but in this case, we're expressing it as pre-selecting from our large space of candidate solutions a very small subspace that we're going to focus on. Now, if I said it's an essential thing, does that mean that once you introduce your bias and you select your subset, you're good to go? No. If you selected the wrong bias, you're doomed. Okay, so there's no guarantees in this world. You have to make assumptions, and if you made the wrong assumptions, you're in bad shape. But nonetheless, you have to make assumptions. I will try to prove that to you. In fact, you're going to do some homework related to that. So our inductive bias would be to choose to use only conjunctions. I'm going to call the space of functions that we're considering the hypothesis space, and give it a letter H. H is the hypothesis space. H is a subset of C. In fact, it's a tiny subset of C usually. Usually it's an exponentially small subset of C. So I will write it like this. The size of H is much less than the size of C. In our case, it was 972 versus 10 to the 30. That's not the only way to introduce inductive bias, but that's the maybe most concrete way and the way we're going to start with. Once you agree to, and by the way, you don't have to use conjunctions. You could choose to use disjunctions. You can choose to use a space that contains both disjunctions and conjunctions. It would have roughly double the number of hypotheses. Or you can choose to include others. But you have to make some choice. You have to reduce from the 10 to the 30 to something much more manageable. Can you represent the function that says yes to everything as a conjunction? I see your head. That's the empty conjunction, right? What about the function that says no to everything? Can you represent the function that says no to everything as a conjunction?
Can you include the same attribute, like could you say sky equals sunny and sky equals rainy?
Right. No. If you could, then you could do that, right? So you cannot represent the function that says no to everything unless you allow including the same attribute with two different values. So I want to allow that function. I want it to be part of my space. I want it to be considered one of the acceptable solutions. So I'm going to extend my, my space of conjunctions. H is going to be all conjunctions plus the null hypothesis. How you represent it is up to you. One way of representing the null hypothesis is to just use the null symbol. You could choose to represent it the way you suggested, which is if you ask for the temperature to be warm and the temperature to be cold, then obviously it cannot be satisfied. Or you can just represent it as the temperature being null, meaning I don't accept any value of the temperature. Whatever the value of temperature, the answer is no. Okay? You don't have to do it only with temperature. You can do it with wind. You can say wind equals null. And both of these hypotheses mean the exact same thing. They mean say no to everything. I call this the couch potato hypothesis, the one that says you don't enjoy sport, period. So in Mitchell's book, he uses a related notation, but the important thing is that it's a single hypothesis that says no to everything. That's the only thing you need to really know. Okay, so now we finally have, is that a quick clarification question? Yeah.
Why is it important to have a null hypothesis?
It's not important conceptually to have a null hypothesis. It is completely up to you what you choose to include. It's important for me for what I'm going to show you next to have it in there. Yeah?
Is that like you have like everything has to be null, but it's just like it's like one of those things.
Any one of those things, any one of the attributes equal to null, it's just a notation. They all refer to a single hypothesis, and the best way to describe it is with a bit vector, and the bit vector has all zeros. Remember this equivalence. Every function can be thought of as a bit vector. Very, very convenient. In this case, because the input space is only of size 96, it's actually a reasonable bit vector. You can hold it in your hand. Okay, so if it has all zeros, that means the output on all 96 possible inputs is always no. Okay, so now we finally have a well-defined mathematical problem. The well-defined problem is you're given a space, a hypothesis space, that has 973 hypotheses in it. You're given 4 trading examples, and now you're asked to find a hypothesis in this space that agrees with these 4. Are we guaranteed that there will be one that agrees with them? Are we guaranteed that there will be only one that agrees with them? No, the answer is no to both. So it could be that we will not find any, that there are none. It could be that there's one, it could be that there's more than one. But let's just say that we're looking to find one if it exists, and we don't care if there are more. How would you go about doing that in a reasonably efficient way? Let me show you one very quick algorithm for doing that. It's called find S, standing for find specific. This is an algorithm that you can call it also the couch potato algorithm. It's the algorithm that says, I'm going to start with the assumption that I don't enjoy sport ever. Now I'm going to look at my training examples. If a training example has the output no, then I don't have to do anything because I am a couch potato. I already chose no. But if the training example is a positive training example, if it says yes, I have to modify my working hypothesis to allow that this one is a positive example. Okay? So I'm going to start with the most restrictive, going back to your comment. Started with the most restrictive, say no to everything, and then begrudgingly modified it as necessary. Here's how it's spelled out in practice. We start by little h is our working hypothesis, and we're going to start by it being the most specific. Most specific means saying no the most. Which is the most specific hypothesis in this space? The null hypothesis. It says no to everything. That's why I wanted it. And then I go over my training examples one at a time. If the training examples is negative, I skip it. Because I'm happy with negative training examples. They just reinforce my belief that I should never play sport. But when I find a positive training example, I now have to take my working hypothesis and make it a little bit more accepting, a little bit more saying yes. And I'll do that by looping over all the attributes of that positive instance and making sure that that attribute is satisfied. If it's already satisfied, do nothing. If it's not satisfied by my working hypothesis, I make my working hypothesis more positive. Let me show you a picture of a walk through this algorithm. This is a really, really nice picture because it shows the relationship between the instance space, which I drew here, or the input space. Instances and inputs are the same thing, and the hypothesis space. Let me explain this notation. This notation is the usual notation for the inputs. This is the values of the attributes, which means each one of them must have a real value in it. It cannot be missing. It must be one of the values that are allowed, and these are the labels. This is kind of a new notation. This is the notation that Tom Mitchell chose in his book for the null hypothesis. That's fine. We made all of them null. This notation, the question mark, means that this attribute does not participate in the conjunction. So another way of thinking about it is it could be anything. This corresponds to the third attribute could be any value. Now, each dot here is a hypothesis, which means it corresponds to a subset of the input space. Remember, functions, binary functions, concepts are bit vectors. They're also subsets. These are all different representations for the same thing. So this hypothesis here, H0, the null one, corresponds to the null subset. The set of all values for which we say yes is null. So therefore, it doesn't have a circle associated with it. But every other hypothesis here corresponds to a subset, some subset of the space. Now, the arrows correspond to binary relations between the functions. And these are relations of inclusion. That means H1 is strictly more general than H0 because it includes some things that H0 doesn't include, but not the other way around. So because functions can be thought of as subsets, and subsets have inclusion relationship, subset relationships to one another, you can think of subset relationships operating on the functions themselves. Remember, functions are subsets, are bit vectors. They're all the same thing. Now, two subsets can be either one included inside the other, or have partial overlap, or have no overlap at all. In this case, we say that subset A is a subset of subset B. In general, if you take any two subsets, A and B, it could be that A is a subset of B, it could be that B is a subset of A, but it could be that they're not related. The subset relationship is a partial order in the sense that it satisfies associativity and anti-commutativity. So it's a little bit like greater than or less than, but with one crucial difference. The greater than relation on the real numbers holds between any pair of numbers. The subset relationship does not have to hold between any two subsets. Whenever you have a partial order like that, let me write the conditions. It is reflexive? No. I think this is so associative. It's A is a subset of B and B is a subset of C. Then, therefore, A is a subset of C. But for every A and B, it is not the case that either A is a subset of B or B is a subset of A. It is not the case. So this is not a complete set, this is a partial order. Because this condition does not hold. Whenever you have a partial order on a set, in this case set of hypothesis, it induces a lattice. And what you see there with the arrows is a lattice. A lattice meaning you can think of it as a graph, a directed acyclic graph. So if you take two hypotheses here, since they're not reachable from one to the other by a directed path, they are not directly related to each other. They would correspond to two subsets that either have partial overlap or no overlap at all. But if you take two hypotheses that can be reached from one to the other via the arrows, let's say from here to here, this means this is a subset. In fact, this is a subset of this. All right, this all big explanation is for the meaning of these arrows and the lattice. Now let's see how the algorithm works here. Remember what the algorithm does. It starts with the most specific hypothesis, and then it skips over the negative examples, and it learns from the positive examples. And the first thing it does is it says the first training example is this one, and it's positive. I have to accept it somehow. I have to modify my working hypothesis to agree with this training example. And I'm going to do it by going one attribute at a time and changing it the minimal way I can to make it agree with this. And the minimal way I can is simply to copy over these values. So because the sky was sunny, I'm going to accept sky is sunny. And temperature was warm, I'm going to accept warm here. So I'm going to end up with a hypothesis here that accepts only a single input. Says yes to a single input and says no to everything else. So I switched from saying no to everything to saying no to almost everything. Okay? This corresponds to this H1 here that captures only this training example. This is the subset of a single training example, a single instance. I then move to the second training example. I notice that it's also positive. I need to further relax my working hypothesis, make it more accepting, make it say yes to more instances, at least enough until it says yes to this one. How do I do that? Well, I notice that it's doing fine on these attributes. There's only one attribute here that is different. And if I have to accept this attribute and I have to accept this attribute, that means I have to kick this particular, if I have to accept this value and this value, this means I have to kick this attribute out of my conjunction. And I do that by changing this normal to a question mark. So now I accept anything here. This corresponds to moving down this lattice to this point H2, which corresponds to this subset that includes x1 and x2 in it. So far, so good. My next step is the third training example. It is negative, so I happily skip it. My next step, I skip it, so H3 is the same as H2. It's exactly the same. And my next step is x4. It is positive. So now I need to make sure that this one is also accepted by my working hypothesis. And I'm going to compare the attributes here to the attributes I have in my working hypothesis. This is fine. This is fine. This is fine because I accept anything here. This is fine. But this is not fine and this is not fine. These two, the last two. So I need to change them both to question mark, namely to I don't care, throw it out of the conjunction. By doing that, I'm moving multiple steps down the lattice. And now I accept this subset, which includes the x1 that I wanted, the x2 that I wanted, the x4 that I wanted, but it also includes some other instances as positive. Is that a good thing or a bad thing? Good thing. Why good? This is generalization in action. Why does it happen? Why can't I, since I'm a couch potato and I'm trying to accept as few days as possible, I'm trying to say no as much as I can, why wouldn't I just draw a circle around x1, x2, and x4?
Because we had training data that was not consistent with that particular set.
We had training that was not consistent. No. The training data is consistent with it. The training data says that x1, x2, and x4 are positive. So all I have to do is find a hypothesis that includes x1, x2, and x4, but avoids everything else. Why shouldn't I do that? My goal is to find a hypothesis that is most lazy, that most tends to say no, but still agrees with the training data. Why not pick up exactly the yeses?
The training data is not exhaustive. There might be some other cases which I want to consider.
That is true. The training data is not exhaustive, but that is saying that my strategy is not a good one, that I should not be lazy, right? But bear with me that I want to be lazy. I want to just say no to everything unless I'm forced to say yes to it, okay? Under those conditions, which is the condition that I specified here, why not just delineate x1, x3, and x1, x2, and x4? Yep.
Your bias doesn't allow you to?
My bias doesn't allow me to. That is correct. Another way of saying it is that there is no conjunction that allows me to do that. My bias does not allow me to pick exactly these things. My bias is the fact that I threw away the vast majority of possible functions, and we're left with only a few. So this is where bias causes generalization. If I didn't have a bias, if every subset of the space was a legitimate answer, I could do that. So this is where the assumption that we made about the answer must be a conjunction makes a big difference. This is what causes the generalization. If we made a different assumption, let's say a disjunction, we would have a different kind of generalization. What do you think about this algorithm? Do you like it? Do you dislike it? What are the good and bad things about it? Yeah.
I get the feeling that it wouldn't work in most situations because if you have a large data set, the data may end up ruling out all possibilities. Also, if you have to classify, let's say we had a person classifying warm, cold, whatever. Some days they might be cranky and say, no, I feel cold, which would then change, the whole input.
Okay.
One way may have worked, may not work that way.
Let me stop you here so I can still remember everything you've said. Two different things. I agree with both. One is, it's not likely to work in practice very well, because if you see lots and lots of examples, it will end up converting everything to don't care, to these question marks, and then accept everything. Okay. The second point you made is that if there was a mistake in the training data, if somebody labeled incorrectly one thing, it's going to screw me up. And both are true. This doesn't deal very well with mistakes, with errors in the training data. It makes very hard decisions very quickly based on single examples. That's true. Yep.
So in this particular training data, we have 3 positives and 1 negative, right? But if we flip the order and we had, say, 3 negatives and 1 positive, then should we ideally be flipping the algorithm to start with the most generic function? Because in that case, we wouldn't really come up with a very good.
The question is, what would happen if the proportion of positives and negatives were reversed and there were mostly negative examples and not positive? Should we do the opposite? Should we start with the most general hypothesis and work our way down? The answer is we could. You could have a algorithm called find most general. And then you can think about that as the sports enthusiast, somebody who loves to go out and play every day, but some days they are being trimmed down. It would be hard to do with the conjunction, with the hypothesis basements of conjunctions, and would make more sense with the hypothesis basements of disjunctions or some other hypothesis space. But in principle, it could be done. I'm looking for advantages and disadvantages of this particular algorithm. Is it fast? It's very fast. Is it guaranteed to converge? That's something we have to ask ourselves. Or could it go into an infinite loop somewhere? Totally guaranteed to converge. Yeah. Is it guaranteed to converge to the right answer? No. Will it know at least if it converges to the right answer or not? Is there a way for this algorithm to know if it converged, whether it converged, when it converged? And let me ask you this, suppose there are some glaring contradictions in the training data. Let's say the same training example is present both as positive and as negative. Will it discover it? No, it ignores the negative examples. It doesn't even look at them. So there's no way for it to know whether it converged, whether it's getting close to convergence. Well, I suppose if all of the attributes are replaced by question mark, then it doesn't change anymore. But if they're not all changed to question mark, we don't know if it's going to happen or not. So it's a pretty brain-dead algorithm. But beyond the algorithm itself, what do you think about the bias? Is it a reasonable bias? Is conjunction a reasonable bias for this problem? No. The point is that this question is not a mathematical question. It's a question about enjoying sport. It's a question about what does it mean to enjoy sport? What does it mean when the temperature is cold? It's a question about the domain, not a mathematical question. But it's a really important question to ask when you design a machine learning algorithm. That's my take-home message. Let me just suggest another algorithm that you're going to be implementing in your assignment. The algorithm that you're going to implement I called exhaustive enumeration. I think Tom Mitchell calls it list then eliminate. And the idea is that you actually explicitly represent all of the hypotheses. And then every time you get a training example, you check to see which of the hypotheses agrees with it. And those that don't agree with it get kicked out of the hypothesis space. So think of the hypothesis space as this onion. This is the hypothesis space. Now it's a circle. It could be a square. It could be all of the concept space, or it could be a subset of it. It doesn't matter. This is exhaustive enumeration. Exhaustive enumeration. Also known as list then eliminate. In fact, instead of representing it as a circle, just represent it as a long list of hypotheses. H1, H2, however many you have. And then loop through your training examples. And for each training example, check each one of the hypotheses. And if it doesn't agree with the label of that training example, you cross it out. You might be crossing out a very large number of them with every training example. That's okay. And then you go to the next training example. And when you're done, you're left with a subset of the original set that agrees with all the training examples. And that's what you wanted. And now you can choose one of them, or you can use all of them. You can vote, take a vote among them. This process also goes by the name version space. The version space, starting with some initial hypothesis space and data, is defined as, okay, I'll call it data D1 through DI, is all members of H that agree with D1 through DI. So this is version space H can call it version space I. So the idea is that every time you add another training example, you go to I plus 1, the version space shrinks because you got rid of more things. And it will shrink more and more and more until you got rid of until you went over all your training data. And then you're left with the version space for the final result is the version space starting with H and using all of your data, all of your training data. So in your assignment, which will be released today, you will be asked to do something like this and this. And you would be asked the important question of what happens if you don't start with any bias. So if you start with H being equal to C. Okay? All right, I'll see you on Wednesday.